All right, the next presentation is on coupling morphodynamic numerical modeling and fiber optic distributed temperature sensing to improve bridge scour prediction. The next presenter is Dr. Celso Castro-Bolinaga. He's an assistant professor in the Department of Biological and Agricultural Engineering at North Carolina State University. He received his PhD and his MS in civil engineering at Virginia Tech and completed his undergrad studies in the civil engineering at the Universidad Católica Andrés Bello in Caracas, Venezuela. And Dr. Castro-Bolinaga's area of expertise includes sediment transport, environmental fluid mechanics, and numerical modeling, with research interest in covering topics such as river resilience, dam removal, stream restoration, and soil erodibility. All right.
Thank you, Paul. All right. I'm going to put this away a little bit because I tend to speak very loudly. So, all right, let me change my presentation. All right, so thank you, Paul, for the introduction. So once again, I'm Celso Castro-Bolinaga. I'm an assistant professor at NC State. Today I'm very excited not only to be back in an in-person conference since COVID started, but also to share with you some of the results of an ongoing project that is looking to couple numerical modeling with fiber-optic distributed temperature sensing to hopefully improve scour predictions at bridge crossings. So this is a project in collaboration with Rebecca Hadley, Chari Seide, and Manmushi Hara, all from NC State University. And I would also like to acknowledge the valuable input from Matt Laffer, Stephen Morgan, Brian Radakovic, and Corey Cavalier, who are part of the hydraulics unit within the North Carolina Department of Transportation and basically formed the technical advisory board for this project. I was also going to acknowledge Scott Hogan. He used to step out of the room, but he was very kind in answering many of Rebecca's questions. So thank you for that. All right, so I think it has been made very clear throughout this conference that scour processes, either those taking place at a bridge pier or those taking place around abutments, as the examples shown in this slide, they still remain a major challenge basically in river drying environments, specifically related to how we predict this phenomena and then how we mitigate this phenomena. Part of this, of the reason why it's still a challenge is the complexity associated with the flow and sediment transport processes that govern the formation and the evolution of these phenomena in rivers, but it's also the lack of field scale data that will actually allow us to critically assess the performance of existing analytical and computational approaches, as well as to understand how can we predict this under rapidly changing flow conditions. So partly to address this last challenge, we have basically devised a prototype that is based on the fiber-optic distributed temperature sensing to monitor bridge pier scour at high temporal and spatial resolution. So the way distributed temperature sensing works is by basically using the fiber optic cables as temperature sensors, basically as a thermometer, and then by measuring the backscatter light that is returning to the sensor after a laser pulse has been sent, then you can estimate what is the temperature along each section of the cable. So this can be as frequent as every second, and this can be as accurate as every few millimeters. So for scour monitoring, our hypothesis is that once these fiber optic cables surround the devices in the river, then the thermal response that we're going to get from the sediment, from the water, and from the air is going to be different. And it's going to allow us to actually differentiate where the water-sediment interface is, and it's going to allow not only to track it, to identify the interface, but also to monitor this evolution during a hydrograph, for example, during a flood event. So the overarching goal of this project was to examine the capabilities of two-dimensional hydromorphodynamic numerical models, and all of this research is based in SRH2D for improving scour predictions at bridge crossings. And to pursue this goal, we devised 3 specific objectives that each one of them target different components of the model. So we have a laboratory experiment where we actually prove the concept of can we construct this device and can we test the ability to track the sediment-water interface. We have a numerical modeling component where we were trying to basically compare the performance of HEC-RAS 1D with SRH2D. and identify what are the hydrodynamics and morphodynamic conditions that will be more critical to account for when you have 2D models available. And then the field deployment is basically oriented to deploy those devices in the field, and then to be able to measure the temporal variation of the channel bed surface elevation during active flow conditions. So if we deploy this device continuously, and then we measure during different storm events, we're going to basically obtain that variation in channel surface elevation as for varying conditions. So first I'm going to talk today about the laboratory experiments. I'm going to show you some of the results that we have obtained in the numerical modeling. The field deployment, actually we installed the devices in the field last week, and as we speak we are actually running the first set of measurements at the bridge crossing in North Carolina. All right, so for the laboratory experiments, we built 2 different prototypes of the Fiber-Optic distributed temperature sensing Scour monitoring devices. And these 2 prototypes are shown here as prototype. Let me check this. Yeah, I'm gonna mess with this. There you go, as prototype 1 and prototype 2. And the main difference between these prototypes is first, they are formed by a different cable. So prototype number 1 basically consists of 2 cables, one fiber-optic cable that is attached to a PVC pipe that is 5 centimeters in diameter, and then a heating element, which is the red cable that you see right here, that basically goes on top. So it has two different cables that conform the same device. The dimensions of the so I'm glad it happened to you. Yes. Otherwise, I was expecting that to happen. So we have this. So the devices have the same height as in diameter, and again, the main difference is the cables and the vertical resolution. And the vertical resolution is given by how tight we can wrap this cable around the device. So the prototype number 1 is a more fragile device because if you have active sediment transport conditions, it can basically break one of these cables, and then the fiber-optic was not as strong, as robust. But it has a lower vertical resolution because you can wrap it much more tightly around the PVC pipe. And then the prototype number 2 is an integrated cable, so you have within the same cable the fiber-optic at the heating element, and then it's it's larger in diameter, so you obtain a lower vertical resolution. But both of these resolution relative to the processes that we're trying to measure is still quite good. And here you see a picture again of the prototype number 1 and then prototype number 2, and you can appreciate the difference in the diameter of the cables. So to test this in the laboratory, we built a small laboratory flume. I mean, this is a tall flume and very narrow. Yesterday I was listening to a couple of presentations where they were showing the Colorado State flume, so this is nothing like those. It's very small and it's actually on top of a table. And the whole idea here is that we wanted to evaluate under certain flume conditions, can we capture where the water sediment interface is and where the water air interface is. So it's basically a proof of concept. Does this work? So here you can see the flume dimensions. As I was saying, is 2.4 meters in length. It's a width of about 20 centimeters, and then the height is the same as the device, 60 centimeters. So we use purified sand. There you go. So we use purified sand with a D50 of 0.15 millimeters, and then the maximum discharge that we could attain with the pump that we have was about 9.5 10 to the minus 4 cubic meters per second. And we did varying flow velocities, but again, the flow velocities that we were able to achieve were relatively low. So the whole idea is if the water is standing or if we're still increasing the velocity, do we see a difference in the ability of the device to actually capture these interfaces? So I'm going to show you the results of prototype 1. They are very similar to the result of prototype 2, and I will highlight at the end what are the main differences that we found. So let me walk you through this slide. So this is the no-flow test. So we just put the device inside the flume, and then we send a heat pulse through the device and then try to see what are we getting back in the DTS sensor. So here you see the device, and here you see the results that we obtained. So in this plot, in the x-axis, you see the mean temperature increase when compared to the initial condition before the heat pulse was sent. Here you see the height along the device. So 0 will be way at the channel bottom, and then 60 will be here at the top. And the red line basically is the temperature gradient that we get from this temperature signal, which is the blue line that goes all the way here. So what you see here is that you have a clear temperature signal difference between the part of the device that is exposed to the air, the part of the device that is within water, and then the part of the device that is embedded within the sand. And what we did is develop an algorithm that basically looks at the temperature gradient, it looks at the maximum value and the minimum value of that gradient to actually locate or detect the sun-water interface and the air-water interface automatically. So the whole idea is that once these are deployed in the field, we can get this measurement relatively frequent, and then the algorithm will just detect where is this interface as it changes with time. And if you see the results, the difference or the gradient between air and water is very clear, so the devices do not have any issue simulating this. And then for the water sediment, you see that there is an error that is quite small between 21.5 centimeters and 20.6 centimeters, right where this interface is. So the next two tests, again, we increased the velocity as much as we could with half the pump open and then fully open, above that we have upstream. And then these are the values that we could achieve. But they weren't enough to actually see a difference into how an increasing flow velocity would affect the performance of these devices. So here you have the same type of figure, mean temperature increase on the x-axis, height of the device on the y-axis. The red is the temperature gradient, and then the blue is the signal, the temperature signal. And what you see is that as you increase the flow velocity, then you have a much clearer difference between the section that is in the water and the section that is in the sand. And you can see that when we compare with the no-flow test, you have a almost vertical line, and then when you increase the velocity, even by small amounts, you have a clear difference between what is in the sand, in the water, and the fraction that is on the sand. And this increase in velocity and this more pronounced gradient basically helps to increase the accuracy of the device. So you see the difference between the water sediment interface for the low flow velocity test, and then you see the difference between the water sediment interface for the high velocity test. So it's much more accurate as we increase it. And we ran the same type of test for prototype number 2, and the results that we got were very similar to this one. So one aspect that was important into deploying this device is how much time we need to basically let the pools reach equilibrium with the conditions so that we obtain accurate results. So if you think about the devices, we send the pools, there is an initial temperature along the device. These pools will progressively hit the device, reach equilibrium, and then it will come down. And the whole idea of the heating period is that it will basically set what is the temporal resolution of these measurements. So if we need 10 minutes for this to reach equilibrium and then get an accurate value, so that will be the temporal evolution that we can actually get measurements. What we saw is that basically for this prototype, you require moderate values around 500 seconds to actually reach conditions where you can have a steady measurement of the water sediment interface and the air-water interface. So this variation that you see here is basically the pools going in, and then you have the steady conditions where the pulse is basically reach a thermal equilibrium with the materials, and then here you have just the pulse going down. So it's a non-steady type of pulse that propagates through the device. And you can see also here that for the air-water interface, it's almost, it's very easy to capture, and you require just very little time to do this. And here is just a table summarizing the water sediment interface with the different measurements. So you have, again, the measure and the estimated, and you see the error for no flow, low flow conditions, and then for the high flow, which is 2 millimeters. So what we saw with the laboratory experiments is that the devices that we developed and tested in the lab, they can actually capture the interface of the air and water sediment for varying flow velocities. And as you will see in the last slide of the presentation, we don't want to capture the air-water interface when we deploy this in the field. We are more interested in where the water sediment interface is, because otherwise the device will have to be relatively tall. And the other important thing to note is that the accuracy can be improved by optimizing or calibrating the interfaces detection algorithm. So we tested this for a uniform material sediment, but the accuracy or these gradients are going to change depending if you have more coarser sediment, finer sediment, if you have a mixture. So that is going to really make a difference between where you capture that interface and how accurate can you actually capture it. As I mentioned, the heating sensitivity was basically the main difference in addition to how robust the cable is. And what we noticed with prototype 2 is that, yes, it's less accurate in a sense vertically, but it only needs about 100 seconds to reach that equilibrium. So you can heat the cable much faster, it reaches thermal equilibrium much faster, and then you have similar type of accuracy at a much shorter time. So actually, the prototype 2 is the one that we decide to implement in the field. All right, so I'm going to change gears now to the numerical modeling approach. And again, the idea here was to compare HEC-RAS 1D with SRH2D at 4 different sites that have different hydrologic regimes, different flow regimes, and different sediment transport conditions, to actually understand what are the parameters, the geomorphic and the hydraulic parameters that affect the vertical, the relative performance of these two modes. Now I want to go back so that I don't leave any. There you go. Yeah. Each one of us will advance how we deal with this. All right. So for the numerical modeling, we selected 4 different sites. So all of these sites are within the state of North Carolina. 2 of them are in the Piedmont region. So Ellerby Creek in Durham, North Carolina, and that was quicker. Okay. So Ellerby Creek in Durham, North Carolina, and then the Tar River are both in the Piedmont region, relatively close to Raleigh. And then we have Middle Creek, located south of Raleigh, which is close to the border between the Piedmont and the coastal plains. And then we have the Roanoke River, which is the largest of the one we selected within the coastal plains. You can see here the mean daily discharge, and you will see the differences in the values, in the magnitudes. In addition to the mean daily discharge, the hydrologic regime that controls these rivers is also quite different. So Ellerby Creek and Middle Creek are relatively flashy streams where you see these events quickly rising up or they are short-lived. You have the Tar River, which I will consider a moderate case within all of this, and then you have the Roanoke River, which is very large, but at the same time it has less variability in the flow. So there is a dam located close to the border between North Carolina and Virginia, the Roanoke Rapid Dams. And since the dam was built, the flow variability in this section is not as pronounced. So you have a relatively steady condition, but you have a large river. And in terms of the grain size distribution that we measure, they are all very fine sand to medium sand with a low percentage of fines, and then you see the difference in channel width. So the idea of selecting these 4 sites is to have variability in terms of how this river behaves, in terms of the flow conditions and how the sediment transport conditions will change. So I'll give you a brief overview of the modeling workflow that we developed. And again, this is a work that was performed by Rebecca Hadley. And you see basically all of the different steps that we follow to arrive to the results that I'm going to show you today, which are based on the hydraulic simulations and the Scour predictions. So basically the main thing that we did for the data collection, model construction, and calibration was we collected a significant amount of data in the field, including flow measurements with ATSPs. We used the jet erosion test to characterize solubility parameters, collected volumetric samples of channel bed material, and we used public sources for the elevation and complement the channel bathymetry. And for the model, we used the one-dimensional geometry as a way to establish the geometry, then export it to the 2D and calibrate the model so that we have similar conditions in both environments, the HEC-RAS 1D and the SRH2D. For the hydraulic simulations, we focus on fixed bed simulations, so no sediment transport at the beginning, and we focus on the variability of the velocity, the depth, and the shear stress. And then what we tested for the Scour predictions is how different types of simulations will be defined to fit basically the hydraulic parameters that go into HEC 18 and how that will affect the Scour predictions. So part of what we're going to do next is actually by using the field deployment, directly compare what is being predicted by SRH2D with what we're measuring in the field. So that's what is coming in the next few weeks. So in terms of the hydraulic characterization, similar to what I did for the prototypes, I'm going to show you the results from one river that illustrate our methodology, and then I'll try to give you a glimpse of how are these variability or how are these results distributed across all evaluated study sites. So what you see here is a normalized characterization of stage velocity and shear stress by normalizing the spatial variability that we obtain with the 2D model by the cross-sectional average value that we have with HEC-RAS 1D. So here are the cross-sectional average values for HEC-RAS 1D predictions. And here what you see is the variable per finite volume predicted by the 2D divided or normalized by the variable for the 1D model. And then on the x-axis, you see the horizontal position looking downstream. So you will go from the left bank to the right bank. And you have how this variability is basically changing. So the main goal of this normalization was, first, we don't have measured data, so we only can compare the relative performance between these two models. And second, how is the spatial variability of SRH2D, which is one of the strength of that model actually affects or changes depending on the different sites. So what we saw is that in terms of you can see an example of that variability. Basically, the maximum values are all predicted close to the middle of the channel in this case. So this is the Tar River, which is the moderate side for a 10-year event. And you see that the maximum values are close to the middle of the channel, but as soon as you start going towards the extents of the water surface elevation, you have a decrease basically in this value. So a variable normalized equal to 1 will be a HERAX-1D prediction similar to SRH. And then you have here the 2D model over-predicting the results for the 1D model and vice versa in the lower section. So to evaluate how this changes across different discharges, we basically look at the variability of that normalized flow field characterization using the max and the median. So the idea is that where we're going to look at the variability of where this point is, and where we're going to look at the variability of the median value of all of these parameters. So the maximum value was going to capture the location and how much is the maximum over prediction, while the median, as the discharge increases, was basically going to capture that effect of the floodplains of the horizontal variability that you can capture with SRH2D. So what we saw, and this is very similar for all of the rivers, is that the maximum value was not really influenced by, or not as pronouncedly influenced by the discharge by the increase in discharge, but the median value did change as the flow started to go into the floodplains and it started to be affected by that roughness. Then we got a higher variability of the median value. So with this additional accuracy that you have with SRH2D, then this offers the opportunity to select what will be the best location, or how can you sort of like understand the influence of that P region to select the inputs for the Heck-18 equation. So across the story bridge size, what we saw is, and I'm showing you an example of the stage. So the discharge did not appear to be a strong driver of the difference between the maximum normalized values, and you can see this in all of the rivers. And then the discharge was most important as flow starting to go into the floodplains, and then you have this variability of the median values. The other thing that we notice is that this is very specific. You have sites where the 2D model is actually under-predicting the variables, and you have sites where the 2D model is over-predicting. So in reality, what controls the applicability of these models, or the expected accuracy of these models, depends on the site. It's very site-specific. So using the Heck-18 equation, we basically feed the equation using one-dimensional and two-dimensional fixed-bed hydraulic simulations. And then for the sediment transport, we basically kept the flow constant and let the model reach equilibrium. So the assumption is that, the assumption that we're using is that the flow, that particular discharge, was going to be present in the channel for enough time so that the cross-section is not going to change significantly. So we use the upstream cross-section, basically output by each one of these three simulations, and then we use that to predict a scour depth using Heck-18 predictions. Again, so all of these results are normalized because we don't have any measurements at this point. So what you see here is the scour depth normalized by the pier width, and here you see the discharge. The blue line represents the Heck-18 predictions using the 1D model. The orange lines is the 2D fixed bed, and then the yellow line is the 2D mobile bed. And this relative performance between 1D, 2D fixed, and 2D mobile, again, is site-specific. What we did notice across the sites is that you increase the discharge. The fixed bed and the mobile bed predictions, they tend to basically to be very similar. And we think this has to be as well with the influence of the floodplains, and as the lower the discharge, the more that variability that you have in the channel and the additional accuracy that you have in the channel is important. And then as you start going towards the floodplains, then they become more of a control, and you have similar predictions for the Heck-18. So this is what I was referring to just a few minutes ago. So again, it highlights the importance of the site-specific conditions. You see sites where the 2D models under-predict, you have sites where the 2D model over-predicts, and then this changes depending on where you are. So the concluding remarks is that with the 2D model, the important thing is that we capture that spatial variability of flow and sediment transport variables, and that we saw the influence of Q basically in driving that spatial variability when you go overbank and you have the influence of the floodplains. And then in terms of the scour depth, the same, the importance of site-specific conditions, and then the difference between the fixed bed and the mobile bed, they tend to be larger at low values of discharge, and then more similar at highest values. All right, so I would like to finish my presentation showing you a little bit of the field deployment and what we're trying to accomplish here. So as you saw with all of these different results, they are all normalized relative to the 1D model because we don't have measurements of Scour to actually validate what we're looking at. So that's where this work enters into the picture. So the idea here is that we're going to measure changes in channel bed elevation using the devices, a larger scale of the devices that we develop in the laboratory to measure that temporal variability of the channel bed. So here you have a picture of two devices installed at Ellery Creek Bridge Crossing. This is in May of 2022. And this accumulation of sediment that you see here is basically to a large amount of debris that accumulated on the upstream pier. So the first time we visited this site, this was completely clear. And this accumulation of debris basically created a shear that deviated the flow, and they created this massive accumulation in the downstream end. So this is actually taking the day that, with the help of NCDOT, all of that debris was removed. Unfortunately, we have a big event right after this, and this is a picture that was taken last week. And you can see here that the debris actually came back. And you see all of the riprap that was placed after NCDOT helped us to remove the debris with heavy equipment. Still, these two devices are installed, and what we're trying to determine here is using two different techniques to monitor this. One is using a passive technique in which you don't heat the cable, but you rely on the water temperature and the soil temperature to produce that temperature gradient. And we expect that to be accurate when you have relatively or phase flow conditions. And then the other technique is the one we use in the lab, where you heat the cables, let them reach equilibrium, and then you measure that over time. So we have a gauge right upstream of the bridge, and by having the devices, then we expect to capture this temporal evolution of the scour at the bridge pier across a different range of flood events. So with that, I know I'm a bit over time, but thank you for your attention. If you have any questions, happy to talk now or after.
Let's take, if you got one quick question while we're setting up for the next one, absolutely do that.
All right. Thank you. Yes?
Have you had any big events come through?
Just minimize that.
The equipment's in, does it survive?
Just indicate.
Yes. Yeah. So actually, the first picture that I showed you in May, we just had a big event before that, and it broke the cables that were hanging from the pier to the top. So last week, what we did with the help of NCDOT is actually created a conduit that goes from the pier to the bridge deck and then to a trailer that we have parked on the side. So now the cables are protected by the deck. So you have, but the devices itself, the cable or the structure, they survive. And that stream is very flashy. So we see a lot of events moving that amount of sand.
All right. Thank you so much.